So hello everyone, welcome to week 7 of the TA sessions. So you can unmute yourself and ask your doubts. So this week we covered computational learning theory and some concepts related to bagging and boosting. So you can unmute yourself and ask your questions, or you can post your questions in the chat.
Sir, can you explain the concept of shattering?
Yeah, sure. So So by shattering, what we so suppose we are given a class of hypothesis function. So this is a class or family of hypothesis, and given a subset or given some data, say D, we want to see whether given a whether there is any subset of the data such that the suppose we have some hypothesis which is drawn from this class of hypothesis H. So we want to see if for all possible labelings of that of the sample. So suppose we draw some sample, we have a sample X which is drawn from this distribution B, and we want to see for all possible labelings. Can we use H to uh, to uh, classify these points, classify or learn the decision boundary. So what I mean by that is, uh, so suppose, so let's take the example that was given in the lectures. So suppose we have 3 points which are arranged in two-dimensional space, and suppose now suppose there are two classes plus and minus. So given these 3 points, so there can be 8 such combinations, right? So this can be plus, this can be plus, this can be plus, or this can be plus, this can be minus, this can be plus, and so on. So like this we have, so if our number of classes is 2 and we are given n equal to 3 points, we have 2 to the power 3 such labelings, right? So
Yeah,
now
right.
sub uh, is there a question?
No, no, go ahead.
Okay. So suppose we say that our H is a linear classifier. Suppose we are looking at classifiers which are of the form of this straight line boundary. So given these points, given however these points may be distributed, we can always draw some lines such that this line can help in classifying between plus points or a positive points or a negative points. So out of all possible subsets of this X, if there is at least one such subset for which, if we take all the labelings, if H can correctly classify all the possible labelings of this subset, then we say that H shatters this H. So we say that H will shatter the space of 3 points in this two-dimensional space in R2. But so then we can say that the VC or the yeah, so that is the concept of shattering. And once we go to shattering, we say that the VC dimension of this class of problems is at least two, because uh, it can sorry, it is at least three, because it can shatter at least three out of at least 3 points. We can have this edge which shatters this space. Shattering means you can say that it can divide the space in the plus points and the minus points. But suppose we have four examples here. Suppose we have four examples, and so then we have 2 to the 4, that is 16 such labelings. Now, can we, so suppose our example is, so suppose this is plus and this is minus. So it is not possible to draw a line or find a linear decision boundary which correctly classifies these points, right? So if we are considering this H to be the to be a linear classifier, then we cannot shatter this space of 4 points. So here we say that H cannot shatter the space of 4 points in R2. So then we say that we saw that your BC dimension was greater than equal to 3, but now we see that it cannot shatter more than 4 points. So we say that the PC dimensions of this of these class of classifiers for this. So let me write it down. So PC dimension for 3 points in R2, for 3 points in R2 for the class of linear classifiers is 3, because it can shatter at least one subset of 3 points, but it cannot shatter the subset of any subset of 4 points. So that is the concept of shattering and how we get the VC dimension from that. From that. Are there any doubts, or do you need some more explanation?
No, this is good. Thanks, sir.
Sir, in second case, what is this VC of H, sir, then? Where we cannot linearly, where we cannot shatter the space.
So, so when we talk about VC dimension, we are talking about VC dimension of a VC dimension of a class of say hypothesis. So here we're considering the class of hypothesis to be linear classifiers. So we say that the VC dimension of this type of, so if you are only considering linear decision boundaries, we cannot, the VC dimension of that is 3. So that is what we mean by H. H is the class. So suppose I say that H is some circular classifier or something like that. So then the VC dimension will be different for that.
Okay, sir.
Hello, am I audible?
Yes, hello.
Hello. Yeah. For the 3 points, we have 2 to the power 3, 8 configuration. And
Yes.
linearly, if we take, there is a possibility we cannot like classify linearly. So what is this VC equal dimension is 3 signifies here? That is physical significance I'm not getting.
Okay. So if our points were, so if our points are like this, 3 points that are spread in R2, and we are talking about linear classifier, then we can say that the VC dimension is 3. But in the same space, suppose we take this example where our we have 3 points again, but now your 3 points are on the real number line. Then suppose we say that our points are labeled in this way. So if our class of functions is intervals, so intervals meaning that so suppose this is an interval, right? Or this is an interval. So then this type of uh, classifiers cannot scatter this space of 3 points in R.
So
If 3
in
points
this
are
case, there is 2 possibilities, like minus plus minus or plus minus plus.
yeah, so when we talk about scattering, we look at all possible configurations. So it can, if our configuration was say like this, so then it is possible to, so then we can say that uh, in this interval it is positive and this interval it is negative, so we can scatter that. But there is but this is also possible, labeling. So
Mm.
this type of classifier cannot scatter this space. So your VC dimension cannot be 3 in this case, it may be 2, because using this box type or this interval type of
So
hyperclass.
those are the dimensions which we cannot settle, right? Those counting are or
Yeah, so
other way.
QC dimension is the maximum number of points for which we can scatter all possible combination or can differentiate all possible labelings of that point.
Okay. So in linear case, there is a like minus minus plus is 1. Other way around plus minus will be like this way.
Can you come again? Your
This,
voice is not clear.
I'm asking that we see dimension case, that the linear case, what the 3 signifies, what kind of combination that the 3 point. Hello.
Yeah, the voice is not clear. Can you please type
Okay.
or repeat it?
Sir, for this
Hello.
interval,
Yes,
Am I audible now?
yes, you're audible.
Hmm. So 3 is that is not I'm getting like 3. There is 2 cases where we not set up linearly, but from where this 3 is coming, like 8 minus 2 6 it should be, or what
No,
is the
no.
combination?
So 3 means, so when we talk about 3, we are looking at all possible configurations of these 3 points. So there can be 8 such combinations of this plus and minus,
Yes.
right? So if your this class of intervals is able to learn a decision boundary for all of these 8 classes, only then we can say that it will shatter these 3 points on the real line. But if there is even one case where it does not cannot learn,
Yes.
so then we can say that it does not shatter.
Yes.
So it will look at all possible configurations of these
Okay.
points.
sir, what is VC dimension for this real line interval which you wrote here? That interval problem.
Yeah. So suppose this is our real line, and so we see that it cannot So if it cannot shatter 3, obviously it cannot shatter 4. So let us look at whether it can shatter 2. So suppose, so if we are talking about 2 points, you can have plus plus, you can have plus minus, you can have minus plus, and you have minus minus. So these are the possible things. So if our H is sort of an interval, you can say that for this example, we can for this example we can for this example you can say that if we have a interval of this sort, so something greater than, oh sorry, so something less than this is plus, something greater than this is all negative. You can correctly classify this using this type of classifiers or hypothesis. So using this, we can say that if something is less than this, it is plus. If something is greater than this, it is minus. Or you can say that similarly, we can say that you can use these type of classifiers or hypothesis also to classify these points. So that means your this class of hypothesis can shatter 2 points which lie on the real line. So then you can say that the VC dimension of H in this case is 2. Is this clear?
Yes, sir. Yes, sir. Understood. Thank you, sir. Sir, can you explain about this ensemble learning?
Okay, sure. So so we so it has you know that it has been discussed that any learning algorithm it will have some, so suppose we are given some learners say L, it will have some bias and it will have some variance, and in the ideal situation we want both of these variance and bias to be low. So ensemble learning what it does is uh, so it will, instead of using only one classifier to learn the function to learn the relation between x and y, it will use different techniques. So maybe it will it will use different data sets or different samples, so different training sets. It may use different algorithms or different classifiers and so on. So there can be a lot of ways to there can be a lot of ways um, to so our final aim is to reduce this bias and variance, and we want to use some other techniques such that this bias and variance is low. So suppose so let me give you an example. So you learned about decision trees, right? So if you remember in decision trees, So if the height of the tree is, if your height of the tree or the depth of the tree is large, height of the tree, then you get some model which is uh, which is uh, which overfits to the training data, right? So that is why we looked into this pruning methods to
Pruning. Yes.
yeah, contain the variance of these trees. Okay, that is these trees have very high variance, but suppose instead of this we have, so this was for one decision tree, we have just one decision tree. Instead of that, suppose we have a lot of decision trees. Suppose we have a decision tree 1, a decision tree 2, and suppose we have suppose we have m such decision trees. So this will give us an output of, suppose this will give us say y dt1, this will give us an y dt2, and so on, and this will give us some output y dt. But because each of these individually, each of these will overfit, so what we do is instead of using only one of these, we take the m of this and we take a weighted average of this. So our final output will be something like uh, I equal to 1 to m y dtm. So what we do is, so before going into it, suppose you do some random experiment. So if we repeat the experiment, so suppose you do your experiment once, it will have some variance, right? So you will not get your expected value. But as you increase the number of times you do the experiment, your variance will be reduced. You will get closer and closer to the mean. So this is what happens in this ensemble learning. So each of these individual decision trees may have very high variance, but if we take the this weighted type of sum, the variance of this is reduced. So even though these individual trees will overfit to the training data, your overall model which you get after summing these each of these models, it will not have that much variance. So this is one example. Another example is a random forest. So in a random forest, what we want, so ma'am talked about these weak learners, right? So we have weak learners, and weak learners are those for which your accuracy is just greater than 0.5, say 0.501, 0.51, something like that. So how to do that? So in weak learners, instead of this decision tree, you have multiple trees, and each of these tree is a very small tree. Suppose it has only one depth of, it has a depth of 1. So you have multiple such trees. Say you have m such or t such trees. So this is your tree 1. This is your tree t. What you do? Suppose you have some. So suppose you have some data coming in, and suppose it has these n features, right? So you will take some of these features and you pass it through your decision tree 1. Then you take a separate set of features and to pass it to decision tree 2, and you carry this do this for each of these t trees, right? Once you get that, then again you combine their outputs using this either this, or you can do some majority voting. So whatever the majority decision have been of these trees. So here, even if this so in this example, it since each of these trees are have very low depth, they will have very high bias, right? Because you're not learning a good function. But once you add these up, it can be shown that these have very low bias, that even if your original hypothesis consisted of random forest, your y is a weighted average of this, and you get some model which it does not have high bias and also does not have high variance. So these types, so these are two techniques where we used this different type of different type of algorithms for learning. So in class we saw bagging and boosting, right? So bagging was like we given some data set D, we create multiple data sets by sampling from D, and we learned using different learners for this. Or you can and then once you get your outputs, you do some weighted averaging, some alpha times yi's of this. So we also looked at boosting. So boosting is also like uh, so whichever examples are easy to learn, we give the probability of those examples are lowered. Whichever examples are very hard to learn, we increase the probability. So those are another way of creating different sort of data sets to learn the model. So ensemble is basically like you are having, instead of using solving only a single problem, you are solving the problem multiple times and combining the outputs of those problems. So your overall goal is to minimize your bias and minimize your variance. Are these examples clear?
Yes, sir. Sir, why do we call it as weak classifiers here?
So
The reason
we
is,
call so because
yeah, please go ahead, sir.
yeah, if you want to answer, you can do that.
Sir, what I understood was whichever classifier where the error is greater than 0.5, then we call it as a weak learner. Is it something like
Yeah,
that?
not the error, the accuracy. You want the accuracy to be greater than 0.5. So if your accuracy is 0. Suppose you have two classes, plus and minus, and you have some things that say it's 0. Accuracy is 0.5. So either or, I mean, each example you can just toss a coin and it is like a random chance, like. So you just want something to be greater than 0.5, just greater than 0.5. So it is not, so if you have a strong learner, it will give you accuracy almost 100%. You don't want that. You just want something, just it is a weak learner that is just better than random guessing. So that is why it is called a weak learner.
Okay, sir. Okay, so the weak learner is something where the accuracy is just greater than 0.5.
Just
So
greater than
such learners, we take it as a weak learner.
yes.
And we are going to combine these weak learners to reduce the low bias.
Yes.
Finally. Okay. Okay, thank you, sir.
So each of these learners will have high bias because their accuracy is very bad. But when you combine them, your bias is reduced.
Okay, sir. Got it, sir.
Actually, once we have three weak learners, for example, and combining them, what will be the accuracy? Is there any calculation for that?
Uh, what will I did not get your question? Can you
Actually, there are three weak learners, for example.
yes.
For each learner, the accuracy is different.
Hmm.
And combining these three, what may be the accuracy?
Yeah, so that will depend on the type of. So in general, these are done to decrease the bias, right? So you will get something. So suppose each of these points have say 0.51, 0.51 accuracy. So in general, the accuracy increases. So I think in the slides, ma'am showed an equation. I forgot the slide number. Let me check. So actually, a training loss, it goes in exponentially to zero once you. So let me the 1 second. So if you for week the slides are week 7. If you look at, I think, slide number 61. So there it is shown that even if your each of these classifiers are just better than random guessing, overall your loss or the training loss goes to zero very fast. So there it is shown that your rate of error is less than e to the power something. So if t increases, your rate of overall the rate of or this error goes to 0 very fast, or this accuracy goes to 1 very fast. So these are some of the guarantees that you get.
Sir, what does this union of two intervals mean on the real line, sir? It is just a 2 points and union of it
Union of two intervals on the real line.
on a real line. Yes, sir.
Okay, so suppose this is your real line, and suppose these are your points. So suppose these you have points are within -1, say, and then you have some points to 0. So suppose you are given these two intervals, right? So suppose this is your set A, this is your set B. So your set A and set B union means you will have all the points from -infinity to -1, and you will have all the points from 1 to infinity.
Infinity.
So
Okay, sir.
yeah, you will have the collection of all of these points.
Understood. Thank you, sir.
Okay.
Sir, how is this voting mechanism? It is just that every learner will vote something and finally that maximum of that is considered as a result. That
No,
is
no.
how the vote.
Voting means suppose you have say 11, suppose you have 11 such learners. So in terms of the random forest, you have 11 such trees. So each of them, suppose there are two classes, plus and minus, and suppose your 5 of the learners will output plus and 6 of the learners will output minus. So here majority of the, so here we are talking about majority voting, right? So the majority of
So
the classes will output 6. So that is why we take this.
okay, sir.
So instead of majority voting, we can also have this weighted. So like it was shown in ADA boost, right? Each of the classifiers is assigned some weight alpha I with that. So we multiply the output with alpha i's and then take the sign of their summation. So that is another way of getting outputs out of this ensemble methods.
How is this alpha I value calculated, sir?
So for this boosting or ADA boost, the alpha, we can derive this formula. So I think it is given by minus half ln. I think it is something like this, if I'm not mistaken. So actually it comes when we try to minimize some loss function, and the optimal alpha comes out to be this value. So these are computed by some calculus. I think
Okay,
it
sir.
is
And this
something.
alpha keeps changing across, right, sir?
Yeah. So your alpha depends on the epsilon of error of the learner that you have. So each time you create a new, you have a new learner, it will have a different alpha related in with respect to the previous ones. It is different
Okay,
for
sir.
different.
Okay, sir.
Yes, hello.
Sir, in this pack model, we have two parameters, epsilon and delta. This epsilon is error, but what is this delta, sir?
Okay, so when we are talking about PAC, so PAC is probably approximately correct. So there are two terms, right? So first of all, you want some hypothesis that is approximately correct, and we want some confidence on this. So suppose we have some hypothesis X, we want that their error is not much, we want that the error is small, we want this to be some with some high probability, and we also so this covers this approximately part, right? So we also want that there exists such hypothesis, and we want that there exists such hypothesis with probability at least 1 minus delta. So let me give you an example. Suppose you have this two-class classification problem. This is your two class. These are the two classes. So so I can say that there exists some hypothesis X like this or like this maybe, such that your error is, you have some approximate it approximates your T hypothesis with some probability epsilon, and your confidence, like how what is your confidence in the model. So that is given by this 1 minus delta. So this epsilon is the probability of error, and your delta is the, or 1 minus delta is your confidence in the hypothesis.
Okay, sir. Okay, sir.
Okay. So Siddharth is asking about the relevant books. So there is, so one of the books. So here are some of the books you can refer to. I think the PDFs will be available online, or you can buy these. That I imagine, Introduction to Statistical Learning by, I think, ST et al. Then another is your probabilistic machine learning, or I think, let me check them. Probabilistic. Yes, probabilistic machine learning.
ಪುಂಟಿ ಮಾಡ್ಬೇಕಂತ ಆಯ್ತು.
By Murphy, and another is I think machine learning by Christopher Bishop. Pattern recognition and machine learning. Right. So and another is, so these are some of the popular books that are, I think the PDFs of these are readily available. So maybe so you will have some good good way to, good introduction to the topics. So another is Machine Learning by Tom Mitchell. So you can, maybe you will find, so PDF for this is available. Even for these also it may be available. You can just check it out in the author's websites. It may be available there. So you can go to these books. So the final exam will most probably be an MCQ type of exam, but I am not involved with that, so I'm not sure what type of questions they will give. You can ask it in the Google group, so maybe one of the TAs will answer that. Yes, if you really want to understand some subject, you have to solve some problems. Also, you may have to look at some of the derivations, like for neural networks. If you really do a back propagation by hand from some example, then you will have some better understanding than this. And if you have any doubts from earlier lectures, also we can discuss.
Sir, the VC dimension not clear.
Okay, let me try.
In some example, it is given as for 2 dimension, the VC of H is 2. Sometimes it is mentioned as 3. In some occasions, it is mentioned that 3 is not possible. I could not understand exactly what is that VC dimension and VC of H.
Okay, so we discussed it earlier, so let me go through it again. So before going into VC dimension, you have to understand what is a shattering. Right? So suppose you are given a class of you are given this class of hypothesis, and you have some sample X from some training data. Then suppose you take a classifier. So suppose I say that I have some linear boundaries, some this straight line. So suppose our points are these 3 points which are in R2. So and if the number of classes are 2, so which is plus or minus, so you can have 2 to the 3 such classes, right? So you can be plus 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 or plus minus 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 plus plus and so on. So you will have eight possible such labelings of data in this form. So if your classifier edge that we had, we have some classifier edge. So for each of these 8 possible configuration, it can classify them whether into positive space or negative space, right? So that means we can say that it shatters the space of 3 points in R2. So here we'll say that the VC dimension of H is greater than or equal to 3. So now let us look at 4 points. We have the same linear classifier. We have the same linear classifier. And now since there are 4 points, we'll have 16 such labelings, plus, plus, minus, minus, and so on. So now so let us look at this example. These two are positives and these two are negatives. Now we cannot draw a line. We cannot draw a line such that it can shatter this into positive class and negative space. So we say that your linear classifier cannot shatter the space of 4 points in R2. So that means your VC dimension can shatter at most 3 points in R2. So we can say that the VC dimension of this linear classifier is 3. So if we can again, like it was given in or shown in the lectures, suppose we have these 3 points in on the real line. So there are if you look at this example and your class of classifier or hypothesis is intervals, then it cannot shatter a combination like it cannot correctly classify a labeling like this. So we say that your H, which is the class of all intervals, cannot shatter this space. But if your number of points was 2, then we can always find an interval which divides it into positive class and this negative class. So hence we say that the VC dimension of this is 2. So VC dimension is basically the number of or the maximum number of points for which the hypothesis class can shatter the space. Shatter means divided into say positive and negative class. Is that clear?
Then what is VC of H? The both are same or VC dimension?
VC is VC dimension, yes. This is a VC dimension of H. VC dimension of H is 2.
then what the number of instances means?
So number of instances means here we are taking only 3 points, right? So here number of instances is 3. Here are only talking about 2 points.
Number of two.
2 can be
So
either plus
if
plus or-
the number of instances and VC dimensions both are same or different?
no, they are
Suppose
different.
I have 2 instances, definitely my VC of H is 2 or
No. If you have if you have 2 instances, and for all possible labelings of these 2 instances, so you have 4 possible labelings here. If your hypothesis can shatter this space, then we said that the VC dimension is 2. Or maybe there may be some example. So as you are looking at 3, like so in this example there cannot be a shattering with this type of hypothesis, then your VC dimension cannot be 3 in this case. So we have to look at a smaller number of points. So then we say that the VC dimension is 2 because it can shatter the space of 2 points on the real line. So this is the maximum number of points that can be shattered by some hypothesis. Is that clear?
yes. Still, there are some confusions, like some cases, if it is a spherical of 3 dimension, the VC dimension is 3, like that is mentioned.
So suppose, let us look at these 3 points. And so there are 8 possible such.
Yes.
So this can
2
be
power
plus
3.
plus plus or 2 plus 3. So if you're talking about spherical, so we can have like all objects inside this sphere are plus and outside is minus. Or we can say that all objects inside this is plus,
Yes.
outside this is minus, or maybe even this case,
Mm.
or even this case. All of these are minus, so we have some sphere. All of these are plus, these are minus. So there is no configuration which cannot be different or classified by a sphere. If it cannot be, then we can say that the VC dimension of this class of hypothesis, which is all those spheres, is greater than equal to 3, because it can shatter this space of 3 points, right? That is what is the significance of this VC dimension.
Oh.
Sir, can you tell the meaning of shattering?
So shattering means you are just dividing your space into, say, positive or negative class. So in this example, you can always use a linear classifier to divide these points into positive or negative class, uh, irrespective of what their labels are. So if you have plus plus plus, you can just say that if you have plus plus plus, you can say that all points on this side of the line are positive and these are negative. Or if you have something like, say, plus plus minus, you can draw a line like this. Or if something like plus minus minus, you can draw some line like this. So out of all possible configurations of these 3 points, you can divide this space for all possible configuration. Then we can say that your edge shatters this space. But here, if we look at intervals, if you have some, say, minus minus plus, then we can have this division. Or you have plus plus minus, then also we can have this division. But if you look at this example, you cannot have this, right? You cannot have some interval which you say that if it is less than this, it is plus, if it is greater than this, it is minus. We cannot say anything like this. So in this case, your interval hypothesis, which consists of only intervals, it cannot shatter this space. Is it clear?
Yes, sir. Understood. So in the VC dimension, we can check the same hypothesis for different set of data set for multiple classes. Is it so?
Yeah, even it can be. It is possible for multiple. So here we are talking about plus minus. So there can be more than one class. Say, suppose you have points like this, and say like this. So if you have some hypothesis of this type, the combination of different planes, and if this is able to separate your points, then you can, so suppose here there are 1 2 3 4 4 3 I think 11 points. So we can say that this type of hypothesis will have PC dimension of 11 if it is possible to settle this space for all possible. So this may be plus, this may be minus, or uh, for all possible assignment of labels to this. So it depends on the number of points for which, for all possible combinations, you are it is possible to divide it into the different classes. Is it clear?
Yes, sir. Clear.
So number of instances, how we can get it? Here you have mentioned that there are different combination. 2 power n is
Yes.
the way.
So
Am I right? 2 power n is the number of instances.
yes, not a sorry, number of instances, but number of possible labels. So suppose I give you 3 points, A, B, and C. Then I say that there are 2 classes, plus and minus. So you can have all plus, all minus, plus, minus, 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 plus, plus. So in this way you will have, so your the 3 points can be any one of these, plus, minus, minus, or minus, plus, plus, right? So that is what we mean by when you say all possible labelings. Because given these 3 points, your data will fall into at least it will be one of these
Out
labels.
of yes, yes.
Yes, yes.
And then what is instances?
Oh, instances is the number of training points you have. So for this case, we are taking only 3 points. Here we are taking 2 points or some, but in training we say we take 100 points, 1000 points. Instances is the number of examples that you have.
Number of examples.
So here, even for only, so if you're talking on linear classifiers, even for only 3 or even for 4 points, a linear classifier fails. So that is why for VC dimension, it is much less than the number of instances that you have. The number of instances can be anything and any subset of the data set.
It is nothing but number of examples.
Yes. Number of training points that you have.
Training points.
Yes.
Suppose number of training point is 10, then number of instances is 10.
Number of instances 10, yes. So for PC dimension, we start from 1 point, 2 point, 3 point, and unless it fails at some point. So suppose there is some hypothesis which have PC dimension say 10,000. So then you can say that for this 10,000 instances, your PC dimension is 10,000, something like that. But generally, this PC dimension for this simple classifiers fails at very small number of instances. This type of classifiers fails for this small number of instances. But instances, when we say, it is a total points that you have.
Sir, can you discuss about ensembles?
Yeah, sure. So generally the learning algorithms that we have seen till now, we have some data, we pass it through a model, and then we get the output. But our overall aim remains to reduce the bias and reduce the variance. So in ensemble learning, what we do is we learn different models, and then we combine the outputs of this model. So in simple terms, suppose you are doing some experiment, suppose, and if you say do the experiment only once, you will get something which is not your exact. So suppose you are tossing a coin, you will not get your expected value, right? So that means you'll have very high variance. So as you repeat the number of experiments, your overall value will come to be closer to your expectation, and your variance is reduced. So the same concept is used in this ensemble learning. So suppose you have many decision trees. So we know that for decision trees, if the height of the tree is large, it will overfit to the training data, and that means it will have very high variance. So suppose we have m such decision trees, and each of these decision tree has very high variance. They are overfitting to the data. But if we take the output of each of these decision trees and we take the average of these outputs, so this model that we get, this will have very low variance compared to each of these individual decision trees. So in ensemble learning, what we are doing here, we are using the same tree on different data to get their predictions, and then we are combining their prediction. So even in random forest, so as it was mentioned in class, we take these weak learners. So weak learners are basically learners whose accuracy is just better than 0.5. We do not want very good learner, we just need weak learners. And then if we say, suppose we have this decision tree of only height 1, so these are not very good decision trees, because your height is very less. And suppose you are given this data, say x, which is n attributes. So out of these n attributes, you take some attributes and pass it to tree 1. You take another subset of attributes, pass it to tree t, and so on. So you do it for t times. Then once you get their outputs, you take a, say, majority voting of this. So these type of models which have much will have much less variance compared to the original models, or much low bias compared to the original models. So similarly, as it was discussed in class, we can divide, or you can sample multiple subsets of the data set and learn individual learners for this, and then we combine these learners, right? Or you have boosting and ADA boost. So the idea of ensemble learning is that you learn it not once but learn it multiple times, and then you combine the output of those multiple results, and then the resultant that you get, it will have very low bias and it will have very low variance, which is what we need.
So when we are
Come again, I did not get you. Hello.
sir, as you said, we have to combine multiple
Your audio, you're not
results.
audio actually.
Audio. Can you hear me?
Yeah.
Sir, as you said, we are supposed to use multiple data sets for the same model and finding the outcomes in different training set, and we are taking a summation of the outcome. Is it so, sir?
Yeah, so so there are different techniques. So like bagging and boosting, they use different data sets as well as different models. So boosting uses different data sets, random forest uses different models. So the basic idea is try to create as many different versions of your problem as possible, and then combine the results.
So when we are combining, we are taking the results of various outcomes of the same
Yes.
process.
Yes, either you take the average
So,
of each of these outputs or do a majority voting of that, or some weighted
okay,
average of that, and so on.
okay. So from that, we are supposed to get low bias and low variance.
Yes, right.
If it occurs in which data set, that will become the better model. Is it so?
Yes, it will be better than each of these individual model.
Okay, sir. Thank you.
Sir, actually, my understanding is a weak learner, each individual weak learner is competent in one part of the
Yes,
one
because
part. Okay.
Mhm.
The combining, then the strength of
Yes,
each learner will be
yes,
combined together.
yes.
But how to know that that particular learner is strong in a particular part of the problem?
So for that, so like we saw here, right? Like we're looking at decision tree of very high depth, large depth. So these models will always overfit to the training data. That is, your training loss will be zero, or accuracy will be very high. So that means it is trying to learn the. It is a very strong learner for that data, but it will not overfit when you take the average of all of this. It will overfit on that specific data set for the specific model, but when you take the average, it will not overfit. It will it will learn better for each of these. So suppose you have some points, say like this and like this on say the 2D plane. So suppose if you have only one linear learner, it will try to learn some decision boundary like this. Actually, this is a good example. Let me give you a different example. There are some more points like this. So in that case, if you just use only one, say only one linear classifier, it will learn something like this, or it will learn something like this, which we don't want. So if we do ensemble learning, so maybe one of the learners will learn this, another one of the learners will learn this. So once we combine this, we'll get a learner which will contain only this decision boundary and not the rest. So that is one of the ways in which ensemble learning works.
Okay, suppose we are using three learners
Hmm.
and by combining three learners, how that model fits, how we can
So for
identify
this,
that. Uh,
for this you do not need three learners like for this example. So maybe you have a third learner which learns also something like this. Then if you take their addition, so it will learn something. So it will have this, it will have this, it will have this. So decision boundary will be something like this, which is still better than a single learner which outputs like this or like this or like this, right?
okay. But can we use different models?
Yes, you
For
can. So
example, you said only linear classifier.
yes, yes,
Three learners are using the same model.
yes,
But can we go with the different models?
yes, sure. So this can be or some like logistic regression. This one can be a neural network. This one can be SVM. You can also use that. So each of them, the only thing is that each of your learner must be independent of each other. There should be no dependency. Other than that, you can use anything you want.
So, so can you tell about bagging and boosting again?
Yeah, okay. So bagging is, suppose you have this data set D. Now you will create, say, some M subsets of this data set, right? So in this example, you are creating 3 subsets of this data set.
Yes,
So,
sir.
if you had some, say, N points, you will have, you will create this data set which has less than N, maybe, or maybe it will be equal to N, but you sample in such a way that the data in each of these is different. So suppose this has 1 2 3, this will have 3 4 5, and this will have 4 1 2. So you create different versions or different samples of this data set. And on each of these data set you learn a different model. So suppose this is one decision tree, you are learning, you're learning a neural network here, you're learning some, say, logistic regression here. So you will have 3 different data sets and 3 different models. So now you have 3 different outputs, right? So this decision
Yes, sir.
tree will output some y1, this will output some y2, and this is output some y3. So then once you get this y1, y2, and y3, you either take a majority voting of this or do an averaging of all of these outputs. So that will be the output of your, that is taken as the output of your model, of your backed model.
Yes, sir.
Is that clear?
Yes, sir.
And boosting, you wanted to, okay, boosting is like, so so think of it something like this. So suppose you are preparing for an exam, and first of all you will cover the whole topic, right? Then after some time you will see that you find some topics easy and you find some topics hard. So that means you will not read the harder, or you will not read the easier topics again, you will go to the harder topics again and again. So that is the, that is what happens in boosting. So suppose you are given some n points, and first of all of these n points will have equal weightage, and you'll learn some uh, classifier or some model on these endpoints. After one iteration, you will see that some of these points are correctly classified and some of these points are wrongly classified. So if these are correctly classified, that means you have, those are easy examples. Now what we do is we increase the weight of these harder examples that were not correctly classified, and then we learn the model again. So then, and the next time again also we'll have some correctly classified points and incorrectly classified points. So at each time we increase the weight of the negatively class or incorrectly classified points and decrease the weight of the correctly classified points. And so suppose we do this for t times, we'll have t such models. Then we take the sum, weighted sum of all of these models. So that is what happens in boosting, or ADA boost in particular.
Yes, sir. Understood.
Sir, general question, sir. Can you hear me?
Yes, yes.
Sir, in the final exam, will we get the questions related to the assignment questions pattern or as a descriptive pattern?
So I am not sure of that, but I think the difficulty level will be of this the same as you got in the assignments. But for the exact pattern, I am not so sure of it. I am not involved in setting the questions. So maybe you can drop a message in the Google groups. So some other TA will, maybe they will
Okay.
explain.
Okay, sir.
Okay.
So where will we apply this bagging and boosting?
So it depends on the problem. If you have if you have some data set where you're not able to get good results, so maybe you can go into this bagging and boosting type of approach. So if you look at this sklearn library, it will have some functions like xgboost. So that is actually a bagging type of approach, or random forest. That is a sorry, these are all boosting type of approaches. So it depends on the problem you have.
So any type of learning algorithm can it suit, sir?
Yes, your base learners can be anything. It can be linear regressor or linear classifier, SVM neural network. It can be anything. The only thing is that each of these classifiers must be independent. That is, your data should be independent of the other. The parameters should be different from the other. But other than that, each of these individual models can be anything.
Yes, sir.
Sir,
Yes, yes.
sir, can you tell about the sample complexity for finite hypothesis space? Only that finite part.
Okay, so so we are looking at pack type of models, right? We wanted
Yes, sir.
so you wanted models for which your hypothesis uh, approximately it approximately learns a classifier with some probability epsilon, and then the confidence you have of this is 1 minus delta. So you want this type of guarantee. Say I want some model which learns something with 99% accuracy, and you have confidence of say 99.9% confidence in the model. So you want to have this type of guarantees. So in order to have these guarantees, the sample complexity says that how many samples do you need to have this, right? Because your data set can be of any size. So it can be of say hundreds of thousands of size. So generally, it is not possible to train on hundreds of thousands of data to get some error or learn a model. Generally, it is possible to learn a model with smaller amount of data. So sample complexity says that if we want to have these type of guarantees, what is the minimum amount of data that we need? So for those, they derive the bounds that are given in, I think that was described in the lectures. So is the
Yes, sir.
intuition clear? Yeah. So if there are no more questions, I guess we can end today's session. Thank you everyone for attending.